Hello, 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 everybody, and welcome back. Welcome back. It's a bittersweet moment here as we're about to start question 25, the very last question on what has been a nice paper, the 2009 Pascal contest. And what have we got? Starting with the input MN, machine A swaps the two, puts out NM. Starting with input MN, machine B outputs M plus 3N and N. And if we put the same input into machine C, we get M minus 2N and then an N. Natalie starts with the pair 0, 1 and inputs it into one of the machines. She takes the output and inputs it into any one of the machines. Okay, so she's free to do whatever she wants with these machines. She continues to take out the output and give the input into another machine. For example, if she starts with 0, 1, she could use B, and so that would output 3, 1. B again, which would output 6, 1. A, which would swap them. C, which would do... Okay. C, which would subtract, so it'd be negative 11, 6. And then we'd add 18, so we'd get 7, 6. And yeah, they get 7, 6 there. Which of the following pairs is impossible for her to obtain after repeating this process any number of times? Now this question looks, on the surface of it, a little scary. It's bigger than your average 25, just in terms of the amount of words. We've got 3 different machines, okay, and she's free to choose any of them. It's not like a pattern question where she does A, then B, then C, A, then B, then C, A, then B, then C. No. We don't have any of that. She can do whatever she wants. She can just put all these numbers into machines A, B, A, and there's a whole lot of variability. So what you shouldn't try and do with this question is fall into the trap of, let's analyze a particular sequence or a particular pattern. What we have to do is understand, well, ultimately, what are the A, B's, and C's? What together are these machines sort of accomplishing? Or what are they doing? Or more importantly, since we're trying to find something that can't be obtained, what can't the A, B's, and C's do? Okay? Now, depending on your level of experience with this, your mind might jump to certain things. So I've been doing math contests. I would likely say more than you have. If you're watching the Pascal, I'm going to reasonably assume that you're less than 15. Let's say less than 16. So I definitely have been doing math contests longer than you. So I've seen a few things, and my mind starts connecting to greatest common divisors. Okay? Greatest common divisors. This is largely because I've, done a little bit of computer programming. And I know, when it comes to computer programming, so the greatest common divisor, in case you're not familiar with it, we'll just do a little mini lesson. This is the biggest number that divides both of your two input numbers. Now, there's a really great way in computers to figure out how to get the greatest common divisor. What you do is you say, all right, greatest common divisor of A and B. First we ask, is A less than B? If it is, then you just tell the person, well, it's just going to be the same as the greatest common divisor of B and A. You swap the two around, not unlike what machine A does. And then, so that's if that, then you tell them, well, it's just going to be this. But if A is the greater of the two, then you just tell them, well, it's going to be the same thing as the greatest common divisor of A minus B and B. And you keep the B where it is. You just subtract. And then if this becomes less, well, you do it again, and you swap them, and it goes a little crazy. Okay? Now, this is a connection I make, and this is not the only way you can make the connection. You don't have to be a computer scientist to understand this, although I might suspect that one of the computer science people at the CEMC might have made up this question. They sneak in a question every once in a while. So there's that connection you can make to it. You could also explore a little bit, and if you try these machines out, and you want to sort of limit your exploring, because there's a lot of different combinations for the machines, and you only have so much time. But if you try it out a little bit, it's not obvious to see, but you'll never get 2 even numbers if you start with 0 and 1. You'll never get 2 multiples of 3 or anything like that. Okay? The reason being First let's say the reason it's not easy to see that is because it's very hard to see what you're missing, what you're not having. Okay, you can play with these machines all you want and say, oh, I can get 7-6, and oh, I can get 18-13. Okay, and there should be a way to get 18-13 and things like that. But it's very hard to say, what am I not getting? What am I not having? Okay, so that's one thing. But I had another point I was going to make. This is what always happens. I get on a rant and I forget because I want to say like 3 things at once. Anyway, not important. So the GCD, it's a nice connection. If we see it, that's great. Okay, if we do see it, how else might we see it as well? Well, notice that if you start to suspect that, hey, I'm not seeing any even numbers or pairs of even numbers, you can absolutely get one of the numbers to be even. What'll happen is, this was the other point I wanted to make. It turns out that you can get any combination, any pair of numbers, provided that their greatest common divisor that is 1. That is, they don't share any factors. No 2s, no 3s, no 27s, no 17s. None of those are in common. Okay? So how else might I suspect this? Well, machine A doesn't really do a whole lot that's meaningful. So I would roughly ignore him. But machine B and machine C, these are adding multiples of n. So if m and n have a factor in common, well, m plus 3n will still have that same factor in common with m, with n. Same with m minus 2n. Okay, we can begin to sort of show things like that. So if we just go back to our notepad, suppose I have a number d, and it divides m, and d divides n. Then if I put this into machine A, I'll get an n and an m, and d still divides both of those. If I put m and n into B, I get m plus 3n and n. Now d divides m, and it also divides n, and so it'll divide 3n, and it'll divide their sum. And d still divides n. Same thing with the minus 2n. So as long as you start with them having a factor in common, you'll still have a factor in common. But wait, there's more. If you have these, the two end result numbers have a factor in common, so if you know that m plus 3n and n are both multiples of 2 or both multiples of 5, then m plus 3n minus 3 times n, which gives me the m that I started with, also must be a multiple of 5 or any d that you start with. Okay? And we can even further, I'm going to stop theorizing for a moment after this, we can even further connect it to my previous knowledge of GCD. How do you do GCDs? You need to be able to just swap the two numbers, and you need to be able to take a difference. Okay, well, what could we do? If I start with mn, and I apply b, I'll get m plus 3n n. And then if I apply c, I'll get m plus 3n minus 2n, which is just m plus n. And if I apply c one more time, I've got that m minus n. This really is doing the greatest common divisor. And that's what you're going to have in common. Now, do you need to write this little justification for yourself? No, it's a multiple choice contest. As soon as you're making the connections and you do a little work on the side to sort of, test your theory or something like that, as soon as you are confident, as soon as you say, aha, that's the concept, that's what they're going for, you don't need to show anyone your work, you don't need to prove it or anything like that. I'm not even really proving it. I'm giving you sort of bare bones in case you want to go ahead and prove it, which would be great practice for, say, a Friar contest. But all we need to do is see the connection and then say, okay, we've got 5 multiple choice answers. Which of them doesn't obey my rule? Okay? Which of them, so in this case, what's the rule? So starting with 0 and 1, that have a greatest common divisor of, well, what's the biggest number that is a factor of both of them? 1. Any output m and n will also have greatest common divisor of m and n is 1. Okay? So if you realize that, if you make this connection, you understand this rule, then you can say, okay, what of my answers doesn't have a greatest common divisor of 1? And so one thing we could do is say, well, hey, there's 2009's here. And 2009 is 7 times 7 times 41. I'm just going to double check that. I was pretty sure. One thing that it's nice to be able to do if you're going to do these contests, they often like to play around with the year. And so it's a good idea to know, say, common factor or the factors of your year. 7, 7, 41, yeah. Or it's good to know if your current year is a perfect square or a prime number. These are just some fun, useful things. And so, okay, 7, 7, 41. So if we're going to have a common factor other than 1, it's probably either going to be 7 or 41 or something bigger. So we just ask ourselves, well, 2009 is a multiple of, say, 7. Is 1016 a multiple of 7? So I grab my calculator. 1016 divided by 7 is, okay, it's 145. Well, maybe it's a multiple of 41. No, it's not a multiple of 41. So these guys appear clear. They don't have any factors in common. So he's fine. And we just go through. 1004, is that a multiple of 7? No. 1004, is that a multiple of 41? No. I move on. Go to 1002. And you can try and be clever about this. Try and, maybe go from the other end if you want to. I think I'll just go to D next. 1008 divided by 7 is 144. Okay. Now, if I wanted to double check that my theory at least sort of holds, I would probably make sure that 132 also is not a multiple of 7 or 41. Just to give me that extra boost of confidence. And it's clean as well. So our answer is going to be D. Okay. Let's go back a page. 108 and 2009. Yeah, their GCD is 7, not 1. Now, how else could I see this? Well, if I understand that greatest common divisor algorithm that I had at the start, okay, that sort of, if one number is less than the other, you switch them around, so the first one's the biggest one, and if not, then you subtract things. Well, that's sort of reversing some machines. So what I'm going to do is show you another way to, realize that this is going to all work out. Is I'm going to create a new machine D that is sort of a combination here. So D So machine D, I'm going to say is, and this is extra stuff. We've got our answer here. The answer is D. I'm just doing it a little bit more because I feel like if you haven't seen greatest common divisors before, then you're going to be sort of a little stuck. Okay, and so what could we do instead? Well, we could sort of try and reverse this stuff. Okay, so what I'm going to do is I'm going to say, well, machine D is going to do. It's going to apply B, and then C, and then C. Okay. No, I'm just B and then C. Just B and then C, I think we'll do. And so what does that do? Well, Mn is going to go to M plus 3n, and that's going to go to M plus 3n minus 2n, n. Okay. And so D takes things from Mn to M plus Nn. Okay. Now, for each of these particular machines, you could reverse the process. So if I tell you I applied machine A and I got an output of Nm, you can very quickly tell me that you must have put in Mn. And if I put in D, if I tell you which numbers I got out from D, so if I say, well, I just applied D and I got out, A and B, it's not that hard to figure out, okay, then you must have started with A minus B, B. Oh, look at that. That's, change these guys to A and B for stylistic reasons. But we're getting those options, or those operations that did the greatest common divisor stuff. So I'm going to say, this is reverse. And I'm going to use a -1 to say I'm going in the opposite direction. Okay, so what could I do? I can reverse these machines, and I can show you that for the other 4, I can get back to 0, 1. So I'll do maybe 1 as an example. So 2009 and, I don't know, let's say 1002, because I know that one didn't work. So I'm going to reverse the D machine and say, okay, well, I must subtract off 1002. So I'll still have 1002. And I'm going to have 1007 here. And I'll still reverse the D machine again. I'll get 5 and 1002 here. And now I'll swap them. I'll get 1002 and 5. And if I reverse the D machine again, I'll get 997 and 5. If I do the reverse of D again, then I can get 992 and 5. If I do it again. So when I'm reversing D, what I'm really doing is I'm doing C and then B again in reverse. And 987 5, and you can just keep going down like this, and I think you can see the pattern. I'll get all the way down to 2 and a 5. I'll swap, get 5 and a 2, and then D again, 3 and 2, D again, 1 and 2, swap, 2 and 1, D again, 1 and 1, D again, 0 and 1. Okay, now if we reverse this, so if I start with 0, 1, and I apply, well, what's D? If I apply B, and then C, B, C, A, B, C, B, C, now I'm down here, so I'll apply an A again, and then a whole bunch of B, Cs, and then another A, and then 2 more BCs, I should get 2009, 1002. Okay, so this is another way you can sort of try and work out what machines could be used. I made D as a sort of a shortcut machine to make the connection to the greatest common divisors a little stronger. I'm not sure that's going to come across to everyone around. I think, again, this is sort of a gotcha question. Either you understood the greatest common divisors already going into this, which it's something you should have seen, but should you have seen it so algorithmically in school? Not really. Part of what makes it a 25. But either you've seen that, or you're a very quick study and you can catch on to little things playing around and exploring with these machines, or likely I don't think you would have gotten this one at all. Okay, so I made my connection with greatest common divisors. I've tried to justify it twice with these machines here, which may have just ended up confusing some of you. Or my connections earlier when I was talking about, well, if D divides M and N, it's going to divide the output of B and things like that. And reversing it as well. But ultimately, at the end of the day, you see the pattern, and then we just needed to factor some numbers at the end. And we got our answer of D, and I think that's all been good. So that closes off the 2009 Pascal contest. Feel free to like or subscribe any parts of the contest, this video, past video. Leave a comment if you had a different way. Maybe you didn't see the GCD connection. I would love to hear a different way. And of course, you can subscribe to be kept up to date to find out when the next Pascal I'm doing goes up. Up next will be the 2009 Fryer contest, another grade 9 level contest, but it requires written solutions. And I think this question would have been perfect for that, although maybe a little hard to justify, but okay. But we'll see what the 2009 Fryer has in store. Thank you guys for watching so much, and I'll see you in the next video, no matter what it is.